different side chains in a polypeptide and proteins. And we discussed about their distant dependence, different types, electrostatic, or dipole-dipole, induced dipole, or dispersion, etc., etc. And also we discussed about hydrophobic collapse, how actually water can play an important role, especially for molecules, proteins, when we discuss about folding in aqueous solutions, right? Okay, so today we'll discuss about slightly general topic, polymers. Okay. Polymers, why this is important is because your proteins are nothing but polypeptides. So if you see the backbone, so the backbone is actually constant and it is a true polymer, right? So you have a C alpha, then you have okay, so this side, and again this side we have NH and CO. Okay, so this backbone, okay, so is actually fixed along the so this backbone consisting of C alpha, carbonyl carbon, and nitrogen is fixed throughout the backbone of a polypeptide. So it's a kind of true polymer, and then side chains will only contribute on the not on the backbone but on the sides. So in this sense, let's say if you have to really calculate, okay, so a length along the backbone, okay, so you don't need any information from the side chains, because whether the side chain is short or long is not going to make any contribution to the backbone. Okay, so if you walk along from residue, okay, residue 1 to, let's say, residue n, okay, so the length, if you walk along the backbone, is called actually a contour length, because you are mapping the contour of the protein. Okay, so that's why it's called contour length. So this contour length is independent of the size of the protein. Okay, whether it is folded or unfolded or any other intermediate conformation, whether it's elongated, globular, it's truly independent of that, because you are actually calculating this length only along the backbone, walking from the residue 1 to the residue n. Okay, so you have to keep that in mind, and typically this we use a lot, okay, in our experiments in the lab, where the length is what actually one of the parameters we directly monitor. Okay, so the contour length is independent of the conformation state of protein. So what are the different conformational states one can think of in proteins? So one is a native state, or the native conformational state, where the protein has a structure which gives its function for most of the proteins. Of course, some proteins don't have any well-defined conformation. So that's one of the conformation, native state. And another conformation is typically denatured state. Okay, so denatured state is a state where the protein is not in the functional state, but this denatured state can be achieved by perturbing the system from the native state using any perturbation. You can think of temperature, you can think of adding a denaturant like urea, guanidinium hydrochloride, or in some cases you can actually change the pH, or any other way you can really think. Okay, so these are the important conformation states, folded state and the denatured state. And sometimes if the protein has any well-defined intermediate states, then you can think of intermediate states. So the contour length is independent of the conformational state. But of course, contour length will not really tell you anything. So it will tell you truly basically the size of the protein. Okay. So if you see, the sequence of the atoms is actually repeating, right? C alpha. So every amino acid has C alpha, nitrogen, and carbon. Okay. And so on these three atoms actually repeat in an order. Okay, so NCl plus C, NCl. So in that sense, now if you know the number of, it's truly repeating like a Homo polymer. Only backbone we are talking about. Okay, so when we say Homo polymer, we don't really take this away. So this is truly a Homo polymer. So if you know the contour length, then you know the size of the protein. Because if you know the length of one unit, then if you divide that by the contour length, you get the number of units. And in other words, okay, so in other words, to calculate the contour length, you need number of residues in the protein multiplied by the length of one unit. Okay, so then you will get the contour length. But this is not going to tell you anything about the conformational state of the protein. It doesn't really tell you contour length, whether the protein is in the folded state or in the denatured state or some other state. Okay, so then we need to really look for properties, okay, which will give you this information. Okay, so let's say if you want to really know in a simplest way, a protein is actually, let's say, in the folded state or in the denatured state. Okay, so you can really look instead of the contour length. So this is one property, which doesn't really tell you the conformational state, but it will tell you size of the protein. So you can look for what is called end-to-end distance. End-to-end distance or end-to-end length. So, okay, so this is different from the contour length in a sense. For example, let's say if you have a polymer, so which is folded, then you have an N-terminus and C-terminus. And imagine the same protein for some reason, okay, so it's in elongated, okay. So this, imagine if this is a folded state, okay, or native state. And this is a non-native state. So it could be native. Okay. So then the native state, typically proteins are well folded, right? Means that they have a well-defined geometry. So you have the same number of amino acids. The side chains are connected in a similar way. They have the same secondary structural elements, and they have the same tertiary contents. On the other hand, non-native state is basically state which is different from this. So it could be any other state. Okay. So here it's not guaranteed that the same contacts are preserved. Okay. So if you see the native state, then this distance, okay, is called the end-to-end distance. So let's label this as okay, R of n. Okay, so R is basically polymer. Okay, so it doesn't have to be polypeptide; it could be just any polymer, and n is just to signify that size of it. So this is your R n. Okay, so this distance, and for the non-native state, this is your R n. Okay, so if I give you now information that I made a measurement on this protein to give you a series of Rn values, then you can say that based on the Rn value, whether the protein is in the folded state or in the unfolded state. So then how do we know that which is the folded state? How to calculate then this distance in the folded state? Any ideas?
Fret labeling. Fret labeling.
Fret labeling is one. Any other way one can get this distance? So any technique which will give you structure will give you this value. Okay. So if you have X-ray structure, XRD, yeah. If you have a structure solved by X-ray diffraction, directly you have all the atomic coordinates, and also you have end-to-end you can achieve. If you have an MR structure, you can calculate. So basically, for the proteins which have a defined structure, if structure is available, directly looking at that will give you the end-to-end distance. And then how to get non-native state distances. Okay, and so this is not a unique value. Okay, because this state is not very unique. So any deviation from the native state. Okay, so then your whole structure changes, and also your Rn also changes. Okay, but mind you, for small conformation or small set of conformations, the Rn might be very similar to this. Okay, means the distance between these two would be same, but the rest of the structure is different. So you have to keep that in mind, that having the same Rn in the native state and native state and the non-native state doesn't mean that they have the same structure. This is only a property which will tell you basically it's very unlikely that you have the same Rn in non-native state. Okay. So this is one way to simply know that your molecules, okay, which are in the native state are in the non-native state. Okay. So second thing is that, so the contour length is proportional to the size. Okay. Proportional, okay, to n is number of residues. The residues are amino acids constituting your protein, right? But here, Rn does not have to correlate. Correlate to n, right? Because you can have a protein structure where the termini could be very close to each other. Okay, so then the protein could be really large. But R, you can have a small protein, or simply take just an alpha helix. Okay, very small. But the N to C distance is very large. Okay, so in that sense, Rn doesn't have to really correlate with N. Okay, but contour length has to be really proportional to the N, because we are calculating along the backbone.
So does that N in the subscript mean something?
N is just to signify number of residues constituting the polymer. Okay. Okay. So
we have to really look for XRD for the calculation of Rn.
Yes. To know that.
So if we are looking for the XRD, XRD itself will tell whether the protein is in a native state or in non-native state.
No, X-ray. Well, X-ray, that's true. But the thing is that that's only kind of, let's say, I would call calibration to know. But in a real experiment, let's say in test tube you're doing. Okay. So where, let's say, you have set up, let's say, for example, using FRET, if you calculate end-to-end distance in different solution conditions. Okay. So then you want to know in all those conditions where you can't make them crystallize. So then you need to know that the conformation. So if you look at the end-to-end distance, let's say FRET gives you in a solution with the different perturbants. So then you can actually calibrate, you can compare that FRET distance calculated by FRET with this value and then say that, so this solution conditions, okay, where actually it's affecting my native state because my Rn is different from the native state. Okay, so this is a kind of comparative. Okay, it's not just you find out this value and but let's say if you want to compare. Okay, you got the point, right? Okay, so this is one important.
Sir, can one use the cryo-EM technique to determine these Rn values?
Yeah, so if you have a resolution where you can get entire structure, okay, it doesn't have to be really atomic at the angstrom level, but even if you have few angstrom level, you can get the overall architecture of the protein where you can really locate true N and C. So then of course you can get it. Okay, so that's what I told you. Any technique, a tool which probes directly the structure, okay, in terms of its location of amino acids will give you this. Okay, so this is the contrasting feature between the contour length, which is proportional to N, but the native state where Rn doesn't have to be correlated. Okay, so then, but can we really even generalize this for, well, proteins are only a subset of large polymer structures. Okay, so coming back to general polymers, so how true is this for polymers? Okay, so let's say we have polymers. Okay, so where we can talk about the polymers are nothing but so let's say n repeating units. Okay, units are monomers, right? Monomers jointly connected. Okay, so let's say if I have to represent each monomer, okay, so let's say as a segment, okay, so which has certain length. Okay, so now, so this is one monomer, and so these are just like how the amino acids are attached at the peptide bond. So these are also, you can have connected units. Okay, so you can have second unit, and you can have third unit, you can have fourth unit, you can have fifth unit, and so on and so on, right? And this is a Homo polymer, means that the same unit is repeating. Okay, so if the same unit is repeating, so then the properties of these units are identical. So one of the properties we can really think of it is the size of the unit. So that's small l. Okay, so that's this unit. Okay, so each unit now are identical, so the length is l. Okay, now imagine the simplest case and hypothetical case where the angle between these units, okay, let's say theta, call theta. Okay, so again I have drawn the polymer in the 2D, but this is a 3D picture. Okay, so now the simplest case or ideal case where you don't have any restriction on theta. Okay, no restriction on theta means that theta can be anywhere from 0 to 180, right? Means that the next unit, this is the first unit, the next unit can be anywhere with respect to this. Only connection between these two neighboring units is the joint. Okay, so this is called a freely jointed chain. Okay, if you put the acronym FJC, so this is a freely jointed chain because there is no restriction on theta. Okay, so like I said, it's hypothetical. You can never really have theta. Okay, so then can we calculate in this case if you have now, let's say n, okay, n units. So let's say, can we calculate this length or n? So this is exactly same as Rn. Okay, that's end to end distance. Only difference now is that, so this is a polymer where you don't have any restriction on the theta. Okay, so theta no restriction means that you don't even worry about the dihedral, okay, because dihedral is automatically comes into picture in this case.
Sir, I had a doubt.
Yes, yes, Anu.
Yeah, since this is a hypothetical structure, why do we restrict our theta to 180 and not 360?
No, why 360? No. So basically, 0 means that it's falling onto the same, right? And exactly opposite is that elongated. So 180 only. You don't need 360. All right.
He's talking about what about minus that angle? Minus 60, let's suppose.
Minus
60.
What's the meaning of minus 60?
Clockwise, anti-clockwise is kind of.
No. So let's say if you take one segment, second segment is connected. Okay, what are the all possible angles you can really think of? 0 to 180 only. I can't really think of negative. Okay, so angle only we are talking about. Okay, so Anup, is that clear or not? We don't need 0 to minus 180 or 180 to 360.
Yeah, like there are like 3 points to make a line, right? So if it is like
No. It's not 3 points. You're missing the point. We have actually two segments, two fixed segments.
Mhm,
Okay,
mhm.
the angle between them, right? So I can think of overlapping the same thing 0, and then completely opening up is 180.
So it can't bend back, right? So completely opening up
No,
is the final state.
back is 0. Imagine you have
Okay,
one
okay,
segment, another segment is overlap, that is 0. That's bending back,
okay.
I call. And then the exactly opposite one is completely open, that's 180. So you don't need
Okay.
to think about 0 to minus 180 or 180 to 360.
Right now you're moving your hand to left side. Can't you move it to the right side and then now you're moving your hand to the left side, right? Can't you
Okay.
move the hand to the right side, like closing it to the right side? Then we will need negative angles, right?
I don't understand what you mean because that's one segment, mine. Okay. Okay. So I have, okay. Yeah, two clusters. Okay. So I have, let's say, one segment. Okay.
Yeah.
And let's say I put another segment. Okay. So now what
Okay.
is the angle between them? 180. You agree?
Yes. Yes.
Let's say I put like this 0.
Okay.
So I don't have to really think about beyond 180 or below 0.
Oh, that's because now the board is blocking you to move in the other direction, right? So if you take it away from the board and then you bend it in the other direction, yeah, that one.
Anywhere in three-dimensional thing, only I have to really think about 0 to 180.
Okay, so the other angle is not required for this model, right?
No, not
Okay,
required.
that's fine.
Because this basically two segments, okay, and they are jointed. And then I have to really think about all possible angles. Any conformation you take, okay, the angle between these two units is only 0 to 180. Am I missing something? 0 to 180, okay?
Okay.
So think about it. So let's say now, in the case of proteins for the well-defined native states, you have a fixed RNC. But let's say now, for the case of polymer,
I think that you might look because see, I'm taking three like this. Okay? So this is one angle. Now, this angle is 60 degrees.
I don't even have to the third segment, right? You are only
Oh, okay, sorry.
okay. So you don't need third segment. Okay. So if you have to think about, let's say, first segment 1, segment 2, and segment 3. Okay, so then the 3, of course, will bring in more complications. But we are talking about only the jointed segments are the neighbors. So in the neighbors case, this, okay, so 0 to 180 is good enough. Okay, so this is called freely jointed chain. Okay, so if this assumption is correct, okay, and theta is truly random, okay, there are no restrictions. How to get Rn10? Okay. So now, because this is random, so if you have, let's say, so many molecules, let's say in your solution, so each one will have its own Rn. Okay. Because unlike in crystal structure where almost all the molecules will have a fixed Rn, but in the case of these are called random polymers. Okay, or random conformation, that means not random. Okay, random conformations. Okay, so random conformations. So then you have what is the largest value for Rn? Okay, so n multiplied by n. This is the largest possible. And what is the smallest possible Rn?
Only L. L. Only L. The angles are 0.
If n is an odd number, then it should be n. And it's an even number, it should be.
Okay, so interesting case. Okay, 0 when
n is an even number.
n is even.
Actually, you can have 0 in
Exactly. Okay. So only for 2 segments you can't have 0 because it's for 2 segments. If it is angle is 0, then it is 0. But of course, the maximum is 12. So for every case, you can have 0. Okay. So 0 is the smallest. Everyone agrees that 0 is the smallest end-to-end distance one can get in a polymer. Okay, so smallest is 0 and the longest is nothing but all the segments are aligned in a line. Okay, so where
Sir?
it is NL. Yes.
Sir, if the distance is 0 means there is no distance. And how the 0 distance is the smallest distance? Because 0 is means nothing, so there is no distance. And how you interpret
No,
this?
no. Okay, imagine if you have a long polymer, okay. So now let's say it's tracing back. Okay, sorry, I'm writing on this. Okay, so like this, so that's your unit 1, and let's say this is unit n, and your ends are actually again colliding. So in that sense, now this distance is 0. Okay, you understood? Okay, so
Then sir, they are then means they are connected.
no. So that's why I'm telling this is a hypothetical case. Okay, so where the endpoints are actually falling on each other. You can say it's connected, you can say it's circular, but we are not talking about the circular polymers. Okay, that will create another problem. So these are the jointed linear polymers. But imagine the first segment, one end, and the last segment, the end, falling on each other. Okay, so that will give you 0. Okay, these are hypothetical cases. Okay, so now, but these are only the limits. You can really call limits. Okay, NL is one limit and 0 is another limit. But each polymer will have a now length means that okay NL and 0. Okay, so everyone agrees. Okay, so far so good, very nice. But let's say I want to measure. So typically when you measure averages, right? So let's see if I have to measure the average of all these things. So what do I get? Okay, that's the question. So if I have to measure, so in the case of proteins, average is just one number, whether you look at one molecule or n molecules of your protein, all have the same thing. So you just divide by the number of molecules you have done, you get the same value, right? But in the case of polymer, okay, each polymer will have any value from 0 to n. So how do I get Rn average value? That's the question. Okay. So how do we go about it? Any ideas?
You want the range?
No, I want true average value.
So one thing is that
Means obviously it will depend on the number of segments, the length of the segment, and theta in a way free. Okay, so basically you have to really tell in terms of the known quantities or the known characteristics or parameters of the chain. Yes.
so let's say you take a polymer consisting of the two monomers.
Two monomers.
Then for a given theta, using trigonometry, we can calculate what is R.
Exactly. Yeah.
And since the probability of having each theta is same, so I think the simple.
So basically, you need to do integration. Okay. So along you assume start with 2. Okay. Assume theta, and then theta is varied from 0 to 180, and n is number is fixed, L is fixed. You can actually get. Okay. But without going to those arguments, okay, can we use very simplistic arguments to get something like this? Okay. So let's say if I treat this as vector algebra. Okay. So each segment now I will think as a vector. Okay. So real vector means that you have the beginning of a vector, you have end of a vector, you can have your coordinate, you can calculate the length and the direction and what. Okay. So now, so the end-to-end distance is also a vector, right? So each segment is a vector. And if you actually project these lengths, okay, so let's say if I take a primer, okay, okay, so then my end-to-end length is this two, right? So this is one vector, and this is another vector, this is another vector. So if I actually project these vectors along dash, okay, so the first point, okay, and the last point, so along this direction you project these vectors, you project this vector, so you will get small piece, and you project this vector, you get this, you project this vector, you get this. So it's a simple vectorial sum of projected vectors onto the vector connecting the end to end, okay, so end to end. So then my end result is also a vector, that's n, right? So which has a direction, right? Obviously the direction line. But if I take all the molecules in solution now, okay, so if I apply now vector algebra, so what will be my Rn? Average of all these vectors means that I have vector Rn. This is, let's say, for molecule 1. So I have another vector, okay, it could be short, okay, Rn2. So like that, I have all the vectors in solution. So what will be my average of Rn? But think about it, you don't need any complex algebra. So you have so many molecules. Each one will have Rn, means that it has a length and direction. A length and direction. But so many vectors are there in solution. Means that you have all possible orientations are there. Means that for every a vector which is along this direction, you want to find another vector exactly equal in length and opposite, because we have so many more. So then what will be the average of Rn?
So
Zero.
0.
Okay, so very simple. You don't need any because we are talking about ideal systems. Okay, ideal systems are always this.
So this is
Good.
also hypothetical.
This is also
Hypothetical.
sorry,
Hypothetical. As you say, this.
yeah. So well, we began with a system where we have segments of a fixed length where they can really bump into each other, but they can actually have very random values. Yes, hypothetically, yes. Okay, average this there. So then this will not be really useful for us. So, but individual molecules are not zero. Individual vectors have certain length, right? Means they are non-zero vectors. So then if you want to really measure the true end-to-end distances, then we cannot simply average. So what do we have to do to get that? Rn is defined as basically a vector here, right? Rn is basically, yes. So Rn is a distance between the first point and the last point. Truly. But here we are talking about vectors. So obviously you have direction comes into picture. So positive and negative are cancelling each other. Okay, because we are taking those as vectors. But using vector things is easy to calculate. But let's say this will be useful. So then what do we have to do so that we can get a meaningful value which truly represents not the directions but the magnitudes.
Sir, I have a question.
Okay? So instead of this, what if we square it? Okay, first square it so that the sign thing will go off. They won't cancel each other. Means that if you have a vector exactly opposite direction, okay, so if you take magnitudes only, then one way is that either you apply mod, okay, where you are interested only in the magnitudes, or simply square. Okay, so this is called root mean square. Okay, so root mean square. Okay, distance.
So that will be the root of this thing.
Root what?
Root means square means square root of this thing. Right? Average of the squares. If we take it under root, then it becomes root mean square.
Yeah.
I think it's mean square. It should be mean square.
Yeah, so let's say mean square. So, okay, mean square. Okay, so now of course, if you take out the square root of that value, that will be your basically average size of your ball. Okay, so that's what actually we are interested in. Either base or root mean square means that, let's say, okay, so this is easy to calculate. You don't need any maths. Very simple argument that because so many molecules, all possible sizes, all possible lengths, so average is simply 0. But then of course, right away you can really tell that this is not going to be 0 because that will be 0 only if individual ones are 0. Okay, obviously it's not true. So there is a non-zero value. Okay, so the question is that how do we get? Okay, so let's say now, so each one, let's talk about as a small vector, small r. Okay, and then so nth segment, okay. So let's now write what we are interested in. Okay, is so how do we get? So basically, okay, Rn is what? Sum of Rn, okay, vector is basically sum of what I said. So if all are parallel, of course, then it's basically okay. So we can. So how do we get? Let's say if each one is small r. Okay. So to get this, one way to think about is that projection, right? So let's say nth vector, okay, and then cos theta, right? So you have Rn projected, so Rn cos theta, and of course sum will go from n to let's say total n. Okay, so that's basically projected value. Okay.
So, we already defined theta as those angles. So would it be okay?
No. So theta is individual ones. Okay. So let's say if we don't get confused, this theta, so we can say prime. Yeah. Good point. Okay. So this theta is different from these ones. Okay. Because that theta anyway variable, so we don't have to really worry about it. Okay, so we need to have basically the projected ones, right? Or can we think about some other way? Okay, so let's say there are another way we can actually do this is so let's see if you take two vectors. Okay, so let's see if you take two vectors. Okay, so what is the sum of this distance? Right, R1 plus R2. So let's say if you are adding another one. Okay, so now you can think of adding these two, right? This is R3. So this is nothing but now R1 plus R2 plus R3, right? And like that, you can actually extend. Means that at a time we are actually adding 2, then 2 to the neighbor, that to neighbor, and so on and so forth. So the final vector is, we know, what is that? R n, right? So Rn is nothing but now summation of vectors. Okay, so this is a vector. So this is nothing but summation of vectors, right? Sum varying from 1 to n vector. Okay, so R n. So simply a vector sum is going to give you either you can really think of projecting individual ones, adding the magnitude. Okay, so that's one way to do. But instead of doing that, simply treat all these as vectors. So by summing the vectors, you get this. Okay, there is a small difference between this and that. Okay, that one is nothing but the projected, but both are same. Okay, so this is good. So let's say how to apply this to R square n. Let's say if you want to measure the squared ones. Okay. Okay, so we can actually apply it to the same thing. Okay. Square. Okay, so this is also mean. Okay, so means that divide by n. Okay, so this is just divide by n.
I think there won't be a bar over that R small r because
No. So this one is finally the magnitude we are talking about. Okay, so once you have let's say a squared length. Okay, so bar means that divided by n. So either you can keep this or you don't have to do that. Okay, so square r we can actually write. Okay, so rn into r. You can write like that as well. Okay, so vectors, but instead of that, I'm just writing the square.
so this is basically the average of
Squares.
yes, squares of those capital R, right?
Yes.
Yeah.
Okay, so intermediate step you can write. Let's say if you dot product. Okay, these are vectors, right? So you have to think about both. Let's say if I have. So what will be its value? This is a vector. This is a vector. Let's say whose magnitude is Rn. Okay, and the same vector. Okay, so let's say AB cos theta. So same. Okay, square. So that's exactly what I'm writing, but I'm putting it on. Okay. So, but this.
Sir, dot product में multiplication vector में angle भी आता है, तो what will be the angle you?
Yes, yes. So these are identical, right? So you can really write Rn. What do we write? Rn into Rn into cos 0, because they are identical vectors. Okay, the angle between the identical vectors is 0. So that will be 1. Okay. Good point. But now, so that is this. So we got this. So the same thing we can write. Okay. So now it is going to be the square. So you write sigma n equals 1 to n. Okay. Sigma. So where again n is going to 1 to n. Okay. So this one. But now, because this is independent from this, okay, so your subscript will be different. Right? Okay. So your subscript will be different because this is different from here. So in this case, we have identical things, so that's why you don't have to worry about cos theta. But now, so if you bring about the sums, n equals 1 to n, m equals 1 to n, right? Okay, so this is a vector, now this is a vector, so here we apply dot product, so the same thing dot product you need to apply. N, m, good, and a dot product. Okay, so subscript n goes from 1 to n and m goes to 1 to n. Right? So now we need to know the angle theta. Okay, so now so again we can simplify. Okay, all the identical terms. When n equals m, you can put one sum. N equals m. Okay, so that how many times n equals to be n m? That will be n times, right? Right. So that will be n times. Okay. So where it is simply r square. Same vectors we are talking about, r square. Okay. So r square. Our magnitude we can write directly. So okay, r is equal to magnitude is basically L, right? So it's basically L into L, or r square for the time being, and plus terms n is not equal to n. Okay, r okay, Rn into Rn cos p, right? Okay, or the dot product. So n times you will get these terms, and this term is nothing but L square. So each vector has a fixed length L. So this is easy. Okay, so we can write n times L square. Okay, and what about this term? Okay, n equals that term. Okay.
This is also the L summation of the particle.
Yeah, but again, think about so many molecules are there. N and M means that any random pair are all random pairs. Zero. Okay, it will be zero because for you take any R, you are bound to have a vector which is equal in length and both in the same direction and exactly in the opposite direction. You are bound to find. So this will be zero because this is an important argument. Okay, so that same thing like we applied that if you take all the molecules, they have all possible orientations. So for every orientation here, you are bound to have one exactly the opposite one. So here also, for every vector, you are bound to have, okay, one in the forward direction,
Sir,
exactly one in the backward direction. So
sir,
it is exactly balanced. Okay, so then you will have zero. Yes?
sir, since the angle is 0 to 180, so if we take average 90, then cos 90 is 0. So can you say that this term also 0 by this way? If we're taking the angle average of the 0 to 180 angle, then it will be 90 degree. Then cos 90 is 0. So this term average will be 0. Can we say that?
Yeah, no. So either you think that's why now theta will be important. Okay, 0 to 180. Okay, so either you divide that. Okay, I have exactly half number between 0 and 90, another half between 90 and 180. So that argument also holds because then you have equal number gives you the positive quantity, equal number will give you the negative quantity. They cancel each other. Or you can really think of that for every vector. Okay, so I have one vector exactly in one direction, the another vector exactly in the opposite direction. That's also fine. Both equally valid. But what you need to understand is that without even going finer calculations, which you can actually do, integration 0 to 180, you can do that. You'll get. So it is 0. So the only term which will be left is this. Okay. So then coming back to, so this is n L square. So what is this quantity n squared by?
Sir,
Yeah.
won't it be divided by n because it's an average? This Rn square bar, this is average of the squares. So won't it be divided by n?
Yeah, exactly. So that's right. You're right. Okay. So here you need to divide this by n.
I mean, if you write
Yeah.
this, then it will be n.
No, okay. So this one will be this. Okay, right. This one will be this. So if I have to really do, okay. So let's say, but we don't have to do average now. We don't have to divide by n. But what's our goal is that true n to n distance is basically now n square root of n. Okay. So basically, if you take any random polymer, any polymer in FGC, freely jointed chain. Okay. So the average end-to-end length is square root of an L. Means that let's say if you have 100 residues. Okay, so of L. So then Rn is equal to 10 times L. Okay. On the other hand, contour length, how much? So for the same polymer, what is the contour length? We have 100
100
residue,
100
100. So it will be 100. Okay. So what it says is that, so now because of polymers, because of their random orientation, so they won't be linear, but they are collapsed. But now you have an average value without even calculating. It is a truly freely jointed chain. If you know the size of the monomer and if you know the number of monomers, you can actually get the average size end to end, because that will tell you about the size. That's basically 10 times length. Okay, and n is actually going to square root. Okay, so now if it is like 10,000, okay, so then Rn is 100 times L, but the contour length is so large. Okay, what it says is that along polymers, when they collapse, okay, so this is how exactly they behave. Okay, so I think you need to understand this. Okay, once you understand this, you can think about now make this model a little bit more realistic. Okay, so right now the each joint, okay, the next joint can exactly fall onto this. Okay, which is not really accepted, right? In reality, you can't really collide. Okay, so the next complex thing is that now you say that my theta doesn't really go back between 0 and 180, but I have a fixed. So which is kind of close to our system, because at the C alpha, you see, because kind of roughly tetrahedral. So your angle is fixed. Your angle is roughly 108, 105, whatever. Okay. So tomorrow next class we'll discuss about how to do the same thing. Okay. So now bring in theta as fixed. So once actually now for that case, if we integrate theta between 0 and 180, we should get this basically, right?
Sir.
Okay. So this special case, if you integrate.
Sir, I have a question.
Yes?
In this, during the averaging of these distances, so why are we taking this as a vectors?
As the
When we are doing the average calculation Rn average, so why are we taking this as a vectors? After all, this is a distance right now.
No, distance, but your argument will really easy to calculate, right? So if I have this, okay, if I know that this is adjacent vector is there, so I know that if I calculate this, okay, interestingly, vector algebra will give you both magnitude and the directions. Directions we have used in a simple argument like this. Okay, so where you know that they get cancelled out, but it's not that we have to use that along yourself. Okay, so you can actually use all the complex integral analysis you can really do, okay, per molecule and then average over all molecules, you will end up getting exactly the same thing. Okay.
Okay, sir. Okay.
So that it's easy, your arguments will be much easier if you use simple vectors.
Okay, sir. Got it. Sir, another question from last class. In the last class, we are dealing with the protein foldings. So when the protein foldings when an unfolded protein goes to the native state, so it must pass through a transition state, right? So is there any method or techniques by which we can visualize the type of interaction which is going on in transition state, or the transition state can get some type of structure which is reflected in the folded state? Is there any techniques to visualize them?
Yeah. So these biomolecules, especially proteins, are their energy landscapes, okay, where we can actually see that how individual states are present or what are the barriers present. Okay, so definitely in the case of proteins, so it's for large proteins, so you always have a barrier to cross, okay, whether from the folded state to the native state or native state to the folded state. So unless you cross this barrier, the molecules will not at any other state, right?
Yes,
Okay.
sir.
So then, how to actually estimate quantities like the energy of this barrier, as well as the structures of the molecules, okay, at the transition state or during the transition state. Okay, so there is no single tool which can give you entire information about this. Okay, so every tool will give you information in bits and pieces. So if you make a kinetic measurements, then you can get the barrier heights. Okay, you can really quantify the energy of the barrier, going from, let's say, from unfolded state to the folded state, or vice versa. Or if you use tools where you can somehow get the information of the interactions, okay, like mass spec. You can actually freeze at different stages of the reaction, and then each stage, okay, so you label what is called deuterium hydrogen exchange, and you quench the reaction. Okay, so typically these molecules now along the energy landscape, they are trapped at different positions, but you can actually analyze them later one at a time. So now, depending on which regions or which surfaces, okay, where the solvent was accessible, okay, where there the hydrogen can be replaced by deuterium. So now, meticulously looking at which atoms are deuterated in the protein, and then mapping that back to the structure will give you which regions have really got exposed during this folding and unfolding reaction. Okay, so there are different methods. Will give you, no single method will give you all the information in single snapshot or instant, but each method will give you some information, so that by using many different tools, okay, and gathering information from all these experiments, you can actually build a model to explain what might have really occurred during that reaction.
Okay,
Okay,
sir.
I hope this class is clear, because we need to practice this. And then simple thing you need to really remember is basically this. The end-to-end length varies square root of n. And this is an important, and this will give you kind of insight. Okay. So let's say what would have happened if you take a protein. Okay. The last class I mentioned hydrophobic collapse. Okay. So where the polypeptide chain basically collapses, where the hydrophobic chains would like to exclude themselves from aqueous environment, so that they clump together. Okay, so during that clump together, now you can really see that, so purely based on a simple random, okay, interactions or random polymer model, because initially they don't have any specific interaction, so the randomly they're actually moving. Okay, so they collapse, and typically the size of that globule will be of this order. Let's say if you have 100 residues in a protein, so roughly when it is collapsed, so this is the kind of diameter you would really get. Okay, so once this forms this kind of globule, random globule, okay, where hydrophobic chains are inside and aqueous chains are outside. Now the finer adjustments will come to picture. Okay, so this could be your collapse could be even smaller than this, because here we assumed that there are no interactions, means that the chains could be slightly extended. Okay, and again you have to understood that this actually falls into that initially we said, right? It's basically NL 0. Okay, so basically square root of NL. Okay, see, this value is in between these two values. I think that you can really appreciate. Yes.
Yeah, actually, I have doubt regarding the calculation. Can you explain? square subscript n bar.
Yeah,
So
maybe
that-
take out this one time. Okay.
Okay, so first we are trying to do what to find out the values of Rn square and this.
Basically, yeah, we are trying to do the dot product.
Okay.
Okay, we know what is a big Rn vector.
Yes.
And because the average of Rn is 0, because all vectors are oriented. So to get rid of that, we are just doing a dot product.
Okay. So from that we are getting that each value of Rn square is equal to n into L square. So this is not the average Rn.
No, no. So this is Rn square.
Yeah.
This is not the average.
Okay. And what are we doing there?
But anyway, so this one is calculated only for one vector. There's no average in that sense.
Okay.
So this is, for example, like one molecule.
Okay.
All right. Okay. So that.
But this particular value, so all the molecules won't be having this value.
No, no. So that's why it's basically the treatment. If you see, okay. So we okay. Okay, let me see.
You put the second term on zero, you have already taken the average.
Sorry.
I think the moment you have put the second term, it was to zero. The positive order.
Oh yeah. Okay. So basically, yes. Here, otherwise you are right. It will be just fixed value. So then automatically, okay. So all either you have divided by n, I guess, right? Means whatever you divide here, you need to apply that. Yeah, you're right. I'm sorry. So this is basically, yes, it's not just for one molecule. Individual molecules will have exactly whatever the value, whatever the value between 0 and 0 and nl.
Yeah.
But this is basically, yes, average of all those values. Sorry.
Okay, so
Correction.
So there should be another n term because what I'm trying to figure out, because if we obtain this value of root n, because this is the result, right? So I guess there will be another n in the picture somewhere in the right hand side, and there will be one n on the left hand side. Because when you are calculating the average, there should be a divided by n. When you are calculating the root, the mean square, then there should be a divided by n. It shouldn't be only the sum.
This shouldn't be.
For example, let's say we are talking about root mean square velocity. So mean square velocity is equal to v1 square plus v2 square plus vn square divided by n. So here also there should be divided by n. That's what I'm
Okay. Or what about if we do this?
I had a small doubt about that. Like, should we actually divide by n? Because if you're dividing by n, that will be like average length per residue. I mean, that does not make any sense, right?
Where?
No. He was
divided by n or only one side?
No, he was telling about when you're taking average, you're supposed to divide by n. So that was a general argument about average, right? But if you're taking divided by n here, it will be like average distance per residue, right? That won't be making any sense, right?
Yeah, I'm also a little confused. Let's see. Okay, so is this correct? Right? So that's some of the vectors, correct, right? So let's say, how do we write this term using this?
So in my opinion, it should be like this: that n into capital N into that mean square part. So n into this thing r square n ka bar. It will be equal to summation part. That's my opinion.
So let's see if we have to write this. Okay, so this one. So then how do we write Rn? Okay, does that work?
इसका sum
So it will be Rn plus Rn of polymer 1 plus Rn.
Yes.
Sum, let's say, okay. So this N will be different, where it could be K or something, or it could be total K molecules.
Yes.
Okay.
K is
So
a
depending on, okay. But then this subscript is same.
Yes.
Right?
Yes.
This subscript is same because you're not really applying individual vectors. Okay, this is fine. K times. So then divided by K.
Yes.
Okay. Okay. So same vector dot product. This vector. Let's say you're applying on K molecules. Then K. So then what will you get here? So that's basically this, right?
Yes.
So then, so this is basically getting cancelled, so it will not even come. Okay. So basically, we are ignoring this. But if we can do this, so that's basically average. But in this way, now we are actually representing. It's nothing but so this is this. Okay. Okay. Here we have this. So again, we can do the same thing. Okay. So this basically either you do by K times divided by K is getting cancelled. So in the end, basically now, okay, okay. Sorry, I think because
Sir, I have a question.
We missed this step, so that's why you got confused. But I think that's all. Yeah.
Sir, so this this formula you did is for Homo polymer. So if we take the heteropolymers or the protein which are different tail, then this formula is work or not?
Okay.
Like
So
we are assuming that all is.
Yeah. So that's why I discussed about in the initially peptide structure, the backbone. If you see, the backbone is identical. Okay, and the length L segment, the L comes along the backbone. For the peptides, it's actually constant. The side chains are different, but the nitty gritties. So now so each L has, for example, let's say each segment in peptide, backbones are same, but the side chains, there is R1 here, there is R2 here, there is R3 here. So these side chains are different. Okay, so these side chains will bring in or remove ideality, because in this case we are saying that they are not interacting or non-interacting. These are random segments. They don't have any specific interactions. Okay, so that's one thing is actually missing. So now if you bring in that my R1 has stronger association with R3, or R3 has stronger association with, let's say, R16, of course, then you have to build that into model. Okay, so any specifics, it's very difficult to build into model, but any generic parameters if you bring in, that will be helpful. So tomorrow actually we will bring in, instead of this R theta is random, now we will actually fix theta. So that's called actually freely rotating mode. Okay, freely rotating chain model R, it's FRC. Okay, so this one is FGC, this is FRC. Where, so just we let theta fixed, okay, so which is a bit more realistic even in polymers and definitely in proteins. So that will see that how that will actually change our end-to-end length. Okay, yeah.
How does it really
Distribution of
look?
R length, real in real systems.
So for a freely jointed chain, let's say plot the distribution of the end-to-end distance. And how does it look?
Okay, that's a good question. Okay. So right now, let's say you want to plot Rn, right? Okay. So for proteins, it's fixed. Okay. So and let's say your contour length is NL, somewhere here NL. So this one is always less than NL. Okay, and let's say your average is square root of NL. Okay, so this could be even sometimes smaller than this or larger than this. Smaller means that the ends are very close to each other. Larger means that ends are really far. Okay, so for let's say interesting question FJC. Okay, how does, so it's not a single value, only we know the average value is this. The question is that if you have measured and made a histogram of the all the end-to-end length, his question is that how does that distribution would look? Okay, good question. Any ideas how it might look like? We already have, that's max. It will never go, any point will never go this. And it can be 0, but we already calculated the average is root NL. So then anyone can guess what might be the distribution look like?
A Gaussian type distribution.
Gaussian type, Gaussian.
Gaussian type distribution.
So basically this is a center mean, but then this length and this length are not symmetric. So it's close to Gaussian, but okay, good question. So that's for proteins, and this is for this. Very few molecules where ends are close, and rarely you have this. So basically, most of the molecules are in this square root. Good question. Yes.
Below the Rn, the distribution is not going to 0, right?
I mean, a small number. That's all.
It's a small number.
Yeah. If you measure billion molecules, you might have just 1 or 2. It could be more. I don't know.
So it is not clear to me exactly what are we doing. This summation, what are we summing up? Is it the average of Rn?
So we are actually doing a dot product.
That part is
So directly jump from here to here. So Rn is this. Another Rn is this. Only thing is that, so okay, so now you will take out the sums. Then you have Rn dot Rn. Only thing is that sometimes they might be same, sometimes they might not be same.
So you get this, the K by K.
K by K is because of this.
Yes,
So,
that there's no doubt because all the summation of small Rn won't be the same.
No, but this is anyway outside, right?
Yes, I'm saying is that.
No, so this K, okay, so what is a K means that so many times you are doing.
Yes, but I'm saying that this capital Rn refers to one student, right?
Yes, correct.
Now there are many molecules. So K is from 1, the number of molecules is from 1 to K.
Yeah.
So there will be one summation of Rn, one summation of small Rn for a
Correct.
particular molecule,
Yes.
then another.
Correct.
So you cannot simply just do K by K. There will be another set of summations.
No, so there's either exactly. So you can do each one. Now we under okay. So each one is Rn square, right?
Yes.
So each one is Rn square. Okay, but this Rn square will be different. Okay, so this sum of the vectors is not same in this or in this. Either you can do all those sums and then divide by k, you will get this, or directly just taking these subsets, you will get this. Okay.
Sir, I have a question.
We are doing this. So here you see, you sum all those terms, k terms. Okay. So let's say such k sets are there. So here it is actually k times divided by k. Makes sense for you? Because these are identical. Right? Again, you have, so these ones coming from all the k sets. If you sum them, is automatically 0, whether you divide by k or not immediately. So these ones are coming from this k times. So that's why all of them are 0, because it's a Rnm cos theta, right? In one case, let's say, no, in one, so this Rn and Rn, both the L's.
The cos theta will anyway, it will be like an integral of cos theta from 0 to
Correct.
pi. It will come up to 0. That's not
So this term is not a problem.
no.
So this term is now k times.
My problem is that this part I understand. The summation of Rn dot Rn. So this will give us the
Square.
mean of the square.
Mean of the square.
Mean of the dot products.
Yeah, mean of the square, correct.
Yes, mean
Of the square.
So now when we are writing this, so sir, basically the on the right hand side it should be a summation of n equal to 1 to capital N Rn vector square, and that k gets cancelled out. You were saying that.
Yes.
So I am asking that how is it becoming that it becomes k times of that? It's difficult to explain.
Okay.
Like this, yeah.
So instead of writing this, okay.
Yes.
Now I have to write this k times.
Yes.
Okay. Plus
This is for a different molecule, right?
exactly. So like that, I have to write everything. Or I can write k.
Yes, sir. My
K.
point is that all of them won't be the same. No?
No, all of them now you take out the squared parts which are identical because are in L.
Yes.
You take out non-identical parts
Yes.
from all these things.
Yes.
That sum will be 0.
So then there should be a bar on this smaller.
Small.
R square cube
This
by
one?
bar number 3. Yes. Then
Yeah.
that should explain it. Yeah.
Correct, yeah. So either you say, what do you want to say? Okay, R dot, you want to literally write, you can do this.
But this will be an average R dot average because we are taking out all these terms and
Correct. And how many times you are taking those terms?
just k times.
K times,
K times.
right?
Yes.
And then we are dividing by k.
Yes.
Okay, so that's why I have done that. So that k cancels.
Yes. Now
And, yeah.
but this should be R square average.
Yes.
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 This should be R square average. Then it's okay.
Okay. But finally anyway. So this
Yes.
is.
Now it's fine.
Okay. Good.
Sir, I have a question.
Yes, Kusha.
So, sir, if we are only considering the backbone and in this model and just not considering the sidechain interactions, so what is the point of considering this term n not equal to m?
No, so let's say I give you, let's say 10 different proteins, So let's say I want you to estimate, let's say all the molecules are actually same size, but different side chains. But I want you to approximately calculate what is the collapsed globule size.
Okay.
How do you calculate? So this will give you estimate about if you take that long polymer. Once it is, okay, non-specifically collapsed, okay, what is the approximate size of those globules? Okay, these are the beginning arguments for your protein folding reactions. So these models will give you estimates. It's not that what you get this value, average value, okay, is the value for your protein. No, your protein might be slightly on either side, okay, but the folded ones are different. But when they are in the unfolded and globules, so their sizes will give you this. Okay, again, see, we are calculating end to end. Okay, and I'm directly correlating that to globule. You should be able to understand that argument, because if these are really random, so all have, let's say, spherical globules, so in some cases they are end to ends very close to each other, but in some cases diametrically opposite. Okay, so you can really see that if all are again random, you can actually calculate that's approximate size is basically integral over 0 to, let's say, 2r, you will get your average value. Okay, so that's what is basically, yes. So your collapsed globules will have a distributed conformations, and all those conformations will have kind of end-to-end lengths like this, but approximately average. That's what actually these models will give you. And these models actually are tested on kind of molecules. Okay, so where you can really think of molecules which are close to ideal, like ideal gases for the gases, Like let's say if you take polyethylene, okay, so where you have only ethylene groups, CH2, so very weak interactions. And if you take really polyethylene of, let's say, 10,000 mR, okay, so you don't have any very specific interactions, and then you can really collapse that, okay, in solvents, and you can actually measure. The larger the molecules, easy to measure, basically hydrodynamic radius, okay, or the size, using different scattering methods you can really think of, and people have actually validated using this, okay. And of course a lot of arguments will come as we go along into the course. There's something called good solvent and bad solvent. We haven't even talked about this solvent yet. We are talking about just ideal chains, and then how this value actually will depend on whether you have a polymer in a good solvent, means that, so it needs to be solvated, means that it wants to be always elongated higher than this value, okay. Or you can really think about bad solvents where actually the molecules want to be more and more collapsed, so then this average might shift. Okay, so these are basically these values, so will give you kind of benchmark and how to actually even think of visualizing, because you can't really calculate or measure these parameters for each and every molecule you can really think of. But if you test these theories on few molecules, which are close to ideal, then you have confidence that so these are the parameters one needs to really think of. And then whenever you make a measurement, and then see that whether you can actually correlate your information coming from the molecules to any of this. Okay. And actually this is important for our lab experiments, because we almost take our molecules, okay, in our lab experiments when we mechanically unfold, especially protein molecules, we elongate, okay. We literally almost take towards the contour line. Okay, we never really reach this because it's entropically, energetically too expensive, but almost very close to 95%, even 99%, we switch the molecules. And of course, you're actually applying a lot of enormous amount of energy onto this, but you release a force, the molecules actually snap back very quickly, and then they're somewhere in this neighborhood, and then they fold back, and then we can really test. So in our lab, actually, this plot is very useful to think about what might be happening at the molecule when you do mechanical perturbation. Okay, so but if you do any other perturbations like pH, temperature, anything, still the molecules are globular. So most of the unfolded molecules actually you can really think of in this neighborhood. Okay, neither here nor here, but here. And then, so most of the things actually, fine refinements do really happen in this regime of end-to-end mixes. Okay, so but what you need to appreciate is that without even thinking about what are the side chains, okay, very simple argument of end-to-end length means the size, not even really the size. Okay, it's only 1-2 points we are really thinking about in polymers, and then how that distance between those 2 points we can actually really implement in estimating properties of the molecules. That's the beauty of polymer physics. Okay, so next class we'll talk about freely rotating chain.
Sir,
Okay.
just a small query. Sir,
Yes.
so sir, when a protein from unfolded to go to the folded state, there is a delay negative, that is the energy interaction. Now, sir, if we give the same delay value that we to the folded protein, then it will go to the same unfolded state or other unfolded state.
No,
Taking,
that's not. Okay, so unfolded states you can actually imagine. Okay, globular states of similar size as the native state. They're not really far from different, but the diversity of the conformations is huge. So they are so diverse that one conformation is different from the other conformation. Even the other conformation having the same end-to-end length, they'll have totally different conformations. So conformational heterogeneity is very, very high. To answer your question in simple manner, so we use what is called energy landscape model. Okay, because now we are here, I will show you a simple graph. Okay, so let's say you have a native state in the energy landscape. Okay, so somewhere here. Okay, so very narrow conformations. But if you try to unfold this molecule, you know, what kind of conformations they might get. So in the energy landscape, so you can really think of a very complex funnel. Okay, so this is a two-dimensional funnel, but you can really think of this in multi-dimensions or 3 dimensions at least. So this is your conformation heterogeneity. Okay, so think about this is end-to-end distance now as a reaction coordinate. Okay, so reaction coordinate, you can really think of any property of the molecule. But imagine, let's say you're talking about end-to-end length. Okay, so now the molecules, okay, so they can be anywhere, okay, both in terms of energy and the conformations. Okay, so energy could be higher. Okay, at the same time, the reaction coordinates in terms of the length might be different. So you have more heterogeneity, okay, in the unfolded conformations. Sometimes people talk about this is conformational entropy. Okay, so the wider it is, the higher the conformation. The narrow it is, the less conformational heterogeneity or unique conformations. Okay, but these are conceptual diagrams. Okay, it's difficult to calculate even for any system the complete energy landscape, because it's a, first of all, multidimensional. It depends on what you're actually trying to probe. You know, with simply we say reaction coordinate, but you can think of any property. Many properties can be used to act as reaction coordinate. Okay, so but most of the time these are conceptual diagrams to kind of mentally visualize how the proteins might be both energetically and structurally present. Okay, I think I'll end class now. So next class we'll discuss about freely rotating chain. Okay. Okay, bye-bye.